I'm recording that, right? Mm-hmm. Yeah, so I can put that up. Yeah, it's just some stuff into. Oh, yeah, because the discussions were around right. You might have I did manage to delete the discussion forum. So annoying. So apparently you used to be able to just copy the whole thing across, but now you can only copy across the first thread. Yeah, but I don't want that. I want everything copied across. You can anonymize it, but I want everything.
Because Brian wants the same. So what we're going to do is run a script through text file. Delete all the names. And make it as a file.
Okay.
Because I'm trying to get the data from them.
Yeah, it's not
database.
Yeah, that's also not ideal because then that's not. It's not.
Basically, what we want is a form that
rolls over. So, yeah. So whether we have
an external one.
Well, I think one way of doing it is just to not change the course every day. Just have it as static. Yeah, that's like for the one I asked you last week. Yeah, you do it as a static one. And
Yes, that's right.
Yeah, but then probably we have to manually enroll students in that.
We can do that in both.
Okay.
The only thing is what we do
student, yeah, they may stay on, right?
Yeah.
And then it just become unmanageable because we do want them to keep access to
Let me see if there's an external version
Yeah.
We can make the internal.
Yeah, so
just like a name.
yeah. Or if every course had two learn pages, one which had permanent content, to link to that. Although we could do it every time if we had these learn pages for the whole year, we could just make within those because they're permanent, they just have a discussion or you can break it down into like just this course, so then it would always stay with that course.
So the courses are there from previous years.
And the discussion, yeah. So that would be a way of doing it. If we just had a.
Exciting. Can you see waiting for? So when I have the distinctive, you stay have courses and you will stay organization.
And to
So you are recording everything right now?
I guess so. Well, I can just go in and edit it when it's done, right?
Yeah, you can trigger it. Alright. Come back and let me how it looks.
Probably not going to be time. We're just going to assume that it's recorded.
Alright. Yeah, it's going to be. So I'll give you a code to this.
Okay. We start at 10 past, right?
Yeah.
Ew. You hear that? You watched this?
Yeah.
Then you're like the half of the class that actually watched it then.
So this is water.
Something you might give us before. Oh, you are doing this course, right? Nice. She's been here so long that I just assumed that. What? You sure that was just me speaking? Just really quietly. Okay, this is about the start time. So I'll just try and stop this playing. So hopefully most of you watched the video that was posted on Learn. If you look at the kind of the chemical oceanography section here, which is kind of there somewhere. There's also another kind of like bunch of videos down there which you can look at. Some of those are relevant. I'll try and draw your attention to those as and when they kind of come up. Okay. The other thing I wanted to point out was there was this kind of doodle poll, which hopefully still works, of when you want my office hours to be. Okay, so when kind of, because I know quite a lot of you are doing kind of very different kind of sets of courses, so it's going to be quite hard to find a time that suits everybody. So if you do that, then I'll try and pick some sensible time. Okay, so there's that, and then also it's not yet up here, but there's a discussions section. Okay, in here, where if you've got questions about the course, you can ask me via the discussion forum. I'll post an answer that kind of everyone can see. And I'll also try and post questions following the lectures, okay? So to give you something to think about kind of outside of lectures. I guess the one more thing that I wanted to show you was maybe in the main course content now. It's in chemical oceanography. If you go to that, and then you go to the exam feedback folder, if you go there, there's this video here, which it's an hour long. Okay, so but it does go over each of the questions in turn. For my part of last year's exam, not giving the exact answer, but giving you kind of a hint of kind of what most people did wrong, what we're kind of looking for, and also some tips on exam technique for doing exams at university. So I do recommend that you have a bit of a butcher's at that. Okay. Okay, so that's still recording, hopefully. Okay, so this lecture will be the first lecture in chemical oceanography. So, but before we start, I need to top up these things that you've got. So first of all, so how hot is that? Oh, that's bearable. So you might have seen this kind of trick before. But this is a demonstration that's got kind of two parts. So the first part, I kind of want to show you that, well, that's probably going to fall off, so that when we put hot water above cold water, okay, the hot water stays on top. Yeah? It's impossible to take that out now without making an enormous mess. But we'll just see how that progresses throughout the old lecture. Give myself some more hotness. Okay, and I just want to put some of these around there. You can kind of see that when you kind of squirt it in, it kind of doesn't mix all the way down, it sits kind of at the top only. Probably not such a great example. Okay, so it's sitting, you've got a nice layer of warm water on top of cold water. You might have done this with Simon before already in the physical oceanography section. So this kind of, it's quite a nice description of how the ocean is. Okay, so the ocean has a nice warm layer on the top of the ocean. Okay, it kind of separates it physically from the deep ocean. Okay, that's important for how much carbon we store in the deep ocean. because deep ocean gets lots more carbon. We'll see why that is in future lectures. It's also important for the nutrient distribution in the ocean. So it's important for kind of where life is and how much life you can have. So this property of the ocean, where the top is, oh, there's timings on the slide, so that's tedious. Okay, so you can see the warm water stays on top. And we'll leave those there for a while. So, right, so where were we? Oh, yeah, so this is a lecture about water. I should probably go back and, so this is my name, Alex Thomas. This is my email address. It's got a K on the end of it. Once again, that's extremely tedious that that's not working properly. And this is my room, 346, so it's on the top floor here if you ever need to come and find me. So today we're going to be talking about kind of basically the properties of water in the ocean. Just to point out that most of the Earth's water is in fact in the ocean. Okay, there are these other kind of reservoirs of water, so most of the water that's not in the ocean is in fact locked up in ice sheets, okay, which is important for a whole bunch of other kind of aspects of the climate system. And then groundwater makes up a huge component of the kind of the fresh water kind of that we have available to us. In fact, it's a significant component of modern sea level rise is the moving of water from groundwater into the ocean, okay, through us mining it essentially. Okay, that's a little trivial factoid for you. So this is stuff that's been pretty much covered in that video that hopefully you watched before. So this is kind of the atomic structure of water. We'll just skip through kind of this. This slide, I wanted to pause on this one for a little bit. Actually, I'm going to stop these timings because this is massively tedious. Okay, so this is the water molecule, and hopefully you'll remember that it's got this charge, negative and a positive charge, and the result of that is these hydrogen bonds between water molecules. And the thing I want to show you on this slide is kind of this thing down here, these clusters of water image, and this is where you basically have clumps of water molecules. Okay, so water molecules don't kind of act independently in water. So these hydrogen bonds tend to make them stick together into large clumps of water, and this is kind of a bit of a simplification. These can be kind of thousands of water molecules big. Okay, so actually, an individual kind of like bit of water is actually quite a large lump of water. Okay, and this gives the water kind of unusual properties. Okay, such as higher viscosity, because you're actually dealing with this much bigger, kind of like harder to move around blob of things, cluster of water than individual water molecules. And we'll see in a bit when we look back at these water things that this is a very important kind of the clustering of water into these kind of larger lumps is really, really important. That's there as well. Okay, so this was all covered in the previous video. Okay, the hydrogen bonds. Sorry about this. This is the. This is the last time I use this software. Okay, so this I think was covered in the introductory video. So it's got this dipole structure that caused this hydrogen bond between the. So most of the rest of the lecture will be looking at some of the properties of water that are due to these hydrogen bonds. So this is a schematic of what the structure of ice looks like. I think this was the last line of the introductory video. But you can see here, so in this case, the sticks here are representing those hydrogen bonds. And those are holding apart the structure of water. Okay. into this kind of hexagonal kind of lattice shape. And this is kind of the idea that the water kind of clumps together into these long, kind of like almost ice-like clumps in water, and then in gaseous, which you can't see because laptop. The molecules of water are just moving around, and the hydrogen bonds don't act between them at all. Okay, so this is a little movie of what we expect molecules to behave like in water. And you can see that the molecules can kind of move around of their own accord, but they are kind of stuck relative to each other, and that's these hydrogen bonds that are acting between them. So these are basically different. The white things in this one are the water molecules, the yellow things are these hydrogen bonds, and they're kind of held in place within the water structure. So even though it's a fluid and the molecules can move past each other, they can't do completely easily. Okay, so this is why water's got kind of a somewhat higher viscosity than other liquids of the same molecular weight, so it's kind of more kind of gloopy than, say, alcohol or other liquids you may be familiar with. Move on to the next slide. So this is kind of a video of what happens when water freezes. So this is basically gradually cooling down. You can see the molecules are moving very, very quickly in the liquid, and as temperature cools down, they get they move a little bit more sluggishly, and you start to form these. In this case, these white things are representations of the hydrogen bonds, and you can see as we start to freeze the water into this ice structure, these are kind of holding apart the water molecules a little bit more than when they were in a liquid. Okay. Okay, so this is these are some quite spectacular ice crystals, and it's this the thing I wanted to show you here was this kind of hexagonal shape of ice crystals. Why snowflakes are six-sided? So these are the crystals in a cave in Siberia, where the ice has been deposited just from the vapor phase, and you get these spectacular crystals forming. And the reason why ice looks so beautiful like this is because of the these hydrogen bonds holding water into the. It's not working at all. No, it's not showing up the ice drive. Stupid. Anyway, so that kind of summarises the phase transitions between these things are in turn mediated by the strength of these hydrogen bonds. So the key things are that because these hydrogen bonds are kind of holding the atoms together a little bit, okay, that makes it harder for them to escape out of the liquid. Okay, so you need to put more energy into the liquid to turn it into a gas, because you need to basically break these hydrogen bonds. So that means that water has this really high really high boiling point. Means that it also has this really wide difference between its melting and its boiling points. Okay, so with most, flick back to find one of these things that wasn't corrupted by this. No, it's not there. This one. So this is a graph showing for different liquids. Okay, what their this is basically the energy you need to turn something into a gas from a liquid, and this is the energy you need to turn something into a gas into a liquid from a solid. And you can see that for quite a lot of these other compounds of similar molecular weight to water, the difference between kind of melting and boiling is actually quite a small amount of energy. Okay, and that's because once you've broken up the crystal structure of the solid, there's not a lot of things holding together the atoms. So, for instance, for the noble gases, neon, once you've broken the bonds that are holding together a crystal of neon, they're really quite free to move, so it's very easy for them to evaporate. But with water, once you've broken apart some of the hydrogen bonds that are holding together the kind of the structure of solid ice in made a liquid, you still have a lot of bonds to break to turn it into a gas. And this is really important because this means that there's a really wide amount of energy and therefore a really wide amount of temperature over which liquid water can can exist. Okay? And being able to have liquid water over a really wide range of temperatures makes it the planet essentially habitable. Okay? Because if the planet gets too warm, we don't want all our water to boil away, because then life wouldn't exist. Or if the planet got too cool, we wouldn't want all of the ice to freeze, because then we would die. So by having a really wide range of temperatures which we can keep water liquid is really, really important. Okay, so this, where the hell does that equation come from? Okay, so ignore this equation that's randomly appeared in the middle of the slide, because it's certainly not on this useless piece of crap the university can provide. Anyway, so having all of these hydrogen bonds, okay, they can also store energy. Okay, so when you heat something up, when you heat up a liquid, or heat up anything, that just makes the molecules vibrate more. That's how things store their heat energy. Okay, and in most kind of substances, that vibration is stored in two ways. It's stored within the actual movement of the molecules around, okay, or it's stored in the bonds within the molecules vibrating. Okay, so if you have another type of bond, as you do in water, if you have these hydrogen bonds, you can also store heat energy in those hydrogen bonds. So that means that you can put more energy into water, okay, and the temperature won't go up as much because that energy is being stored in different types of bond vibration. So this gives water what we call very high heat capacity. So it's basically it's the capacity for, or the ability for the water to store heat energy, and this is really, really important. Okay, so this is a map of sea surface temperature. Okay, and you can see in the tropics here. Okay, so the Earth receives a lot of energy from the sun. That warms up the water. Okay, you can see the polar regions are quite cold. Okay, and because water has this really high heat capacity, it means that the oceans are really efficient in moving this heat polewards. And you can see the temperature gradients moving from north and south. You can see that in a little bit more detail here. So this is the Gulf Stream kind of disappears off the end of the image here because I don't know why this has gone wrong. But in mine you can see the Gulf Stream. It's basically it's a river of extremely warm water that's transporting heat up to the high northern latitudes. And it's able to do that because of the hydrogen bonds in water are able to store the heat in the water. Okay. So, kind of see the graph it's supposed to be. We've demonstrated at the beginning that the temperature of the water determines its density. Okay, so warm water is more dense than cold water. No, that's wrong. Warm water is less dense than cold water. Okay, which is why the red water is kind of floating on top of the clear water in your glasses there. Okay, and this is really important. Okay, because this means that as water cools down, okay, it gets denser and denser and denser. Okay, which means that as you're, for instance, as you're cooling the surface of the ocean, okay, you cool the surface of the ocean, that water gets denser and denser and denser and sinks away from the surface of the ocean. So it kind of inhibits freezing of the surface of the ocean. Okay, because as soon as the water gets cold enough, it starts to sink. Okay, and you can only change the surface of the temperature of water at the boundary. So you can only exchange heat out of the ocean at the surface. Okay. Water does have this kind of slightly strange property, as that when you get closer and closer to 0 degrees Celsius, pure water actually starts to get a little bit less dense. And that's because these clumps of water that are behaving basically like a little bit like ice. So they're being held, their molecules are starting to be held apart more and more by these hydrogen bonds. So as temperature goes down, these clusters start to get bigger and bigger and bigger. So that means at lower temperatures, water becomes more viscous. Okay, and it also starts to become a little bit less dense. Okay, and this is actually really important for lakes. Okay, because lakes are actually quite small bodies of water, and that means that when if you're cooling the surface of a lake, okay, and and as you cool it down towards 0, the water starts to get more dense, and it will sink to the bottom of the lake. Okay, but the lake's not kind of that big in size, so eventually the whole lake could that water that's sunk to the bottom of the lake would be replaced by more water that's sinking down, and the lake would get colder and colder and colder, and the whole lake would freeze. Okay, but what happens is that in freshwater environments, as you cool down lower and lower and lower, you get towards 4 degrees Celsius, and if you cool down any more, the water starts to become less dense, so it stays at the surface. So that makes it easier to freeze the surface of the water. Okay, so in lakes, it's very easy to form a surface area of ice, where in the ocean, it's very difficult. Okay, but this means in lakes, that means the bottom of the lake is isolated from the surface cooling effect. So this actually keeps, in lakes, it keeps the surface frozen and the deep part of the lake unfrozen. Okay, but in in seawater, in the ocean, it actually, this property doesn't actually exist. Okay, so if we go, okay, so water reaches its maximum density at 4 degrees Celsius. And when we come on to discuss the properties of salt in seawater, we'll find out that this property, that the densest water in the ocean is not at 4 degrees Celsius. Okay, so we're going to talk a little bit now about why, what happens when we put salt in the ocean. So one of the really cool properties of these water molecules is that they have these polar charges on them. So one end is slightly positive and the other end is slightly negative. So we have, say, a crystal of salt. Okay, what happens is, in fact, if we, hopefully, this will, have to turn her off. She's quite annoying. Okay, so this is basically a salt crystal, sodium ions, chlorine ions. The water molecules come on, and basically the charge on the water molecule starts to neutralize the charge in the crystal and can basically pluck off the individual ions. And when they do that, they tend to surround them. Okay? So your positive charge of, say, your sodium ion gets surrounded by the negative charges of the water. Okay? And that basically protects that ion. So it can't then see another chlorine ion, it's a sodium ion. So it means that it can't then recombine and form a salt crystal again. So this makes this polar nature of water, and this clumping around dissolved ions, makes some ions that are ionically charged, or so ionic salts, they make them very, very soluble in seawater. So one of the reasons why the ocean can store so much salt in it is because the water molecules are polarly charged at each end, and they clump around the ions and basically protect them from, they're like an overprotective father. They protect the ions from interacting with other ions. Okay, so water is really good at dissolving salts. Okay, so if we go now and think about what is this effect of these dissolved salts on the formation of ice and the cooling of water. So if we go back to our diagram here, and actually I'm going to draw it because this happens to. So this diagram keeps on disappearing off the top up here. Looks something like it's got. Let's use this. Okay, that works. Okay, so we have density. Okay, rho. Okay, so this is more dense. This is about 1. Okay, and this is temperature. Okay, so with most liquids, in fact, as the temperature goes up, density goes down. It becomes more buoyant. So we should have a graph that looks like this, right? Okay. Now the weird thing with water is that at 0 degrees C, okay, it turns into ice. Yeah, which is actually less dense. That's kind of somewhere down here. Okay, most solids are more dense than their component liquids. But actually, the weird thing about water is that as you get slightly closer to zero, we start to get this clumping effect into these large groups of kind of water molecules, and that starts to hold them apart from each other by hydrogen bonds, reducing the density. Okay? So there's this point here, which is kind of like the maximum density of water is 4 degrees C. Now this is for pure water. Okay? So if we go to this diagram now, so instead of temperature on the bottom, we've got salinity. So this is no salt. Okay, so this is pure fresh water, and this is very salty water. Now the orange line on this diagram is the temperature at which that water freezes. Okay? So you can see fresh water, that freezes at 0. But as we add more salt to the water, okay, we're basically adding ionic strength to water, adding lots and lots of charged ions, and those charged ions are basically stopping these clumps of water from forming this large open structure, okay, of the ice crystals. Okay? So that means that you have to get colder and colder and colder to actually freeze the water. Okay? Now the red line on here is this point here. It's the temperature at which you reach maximum density. So for fresh water, you reach maximum density just under 4 degrees Celsius. But as you increase the salinity, as you add more salts, this temperature of maximum density, okay, starts to go down. Okay? And this is because the dissolved ions are essentially disrupting the formation of these large networks of hydrogenly bonded water clusters. Now the interesting thing is that the ocean is now up around 35 parts per 1,000, I'll come on to the units of salinity later, salt. And at this amount of salt, we never, as we cool down, so if we imagine we were seawater, we started at the top, we're coming down, cooling down, we get to this point here, we've frozen the water before it gets to its maximum water density. Okay? So this means that we never have this situation in the ocean where cooling down water makes it less dense. Okay? So in the ocean, if we cool the surface of the ocean, it will always get more dense. So it will always sink away from the surface before it has a chance to freeze, which makes it really hard to freeze the surface of the ocean, which is kind of really good because having a nice liquid ocean is kind of good for kind of fish living around it. It's good for light getting into the ocean so phytoplankton can kind of survive. So this property of seawater being different to freshwater is quite important. Okay, and I'll just show this diagram. So this is kind of an extension of that diagram. So before we were looking at parts per 1,000 salts. So on the bottom now we've got pure water at this end, and this is kind of 100% salt kind of off to this side over here. And we were just looking at this kind of tiny little corner up here where this red line is, where you reach the maximum density as you cool down with a small amount of salt. So this diagram might be familiar to some of you that are on the kind of the geology degree program. This is a phase diagram, but this is basically showing you as you cool down liquid water, you eventually get to this line here where the water starts to freeze. But if you've got some salt dissolved in that water, the water won't be completely frozen. There'll be some mixture of liquid and salty water. Okay? And the proportions of liquid and salty water depend on where you are and how salty it is and how much you cool down. But basically the thing I want to show here is that, and this is why we add salt to the roads, okay? Because it basically stops the water completely freezing by adding some salt to the roads. I've got this diagram here because at 21.1 degrees Celsius, it doesn't matter how much salt you add. You can have any amount of salt. Okay, and this field here doesn't have any water in it, so it will never melt. So this is why in countries like Canada and Russia, where it commonly gets down below -20, they don't salt the roads because it will have no effect. It will just make their roads salty. Okay, and still slippy. Okay, so this kind of summarises that, which is, I guess, for people that haven't turned up to the lecture. And critically, the addition of salt is modifying some of these properties of maximum density, okay, melting temperature. So I want to just talk a little bit now about diffusion of stuff through seawater. So hopefully, if you can look now at your glasses, okay, you can see that the red hasn't stayed at the top. Okay, it's moved down. Okay, and this is first of all, this is a property called diffusion. So, there was a nice GIF over to the side that you can't see over here. But basically, if you start out with a high concentration of something on one side of a liquid, or in fact a solid sometimes, and you leave it over time, basically that will diffuse along that concentration gradient. Okay, will be gradually mixed out. Okay, so the concentration is equal. Okay, so if I started out with say this one here, we sort of red at the top and clear at the bottom. Leave it over time, the red dye will want to mix completely. Okay, and this is the same not just dye in water but also temperature. Okay, so if you have maybe a metal bar, okay, and you heat one end of the metal bar, okay, the conduction of heat from one end of that metal bar to the other end of the bar, that's just diffusion of heat. Okay, it's going from a high temperature to a low temperature, and energy will always diffuse down that gradient. Okay, so what I want to talk about here is this unique property of water, which hopefully, if you look closely at some of your glasses, you can't see that the red hasn't just moved down gradually. Okay, it's moved down in kind of fingers. Yeah, and if you look at the one at the front here, it's kind of really quite spectacularly kind of gone down in looks like kind of hanging down vines. Okay, so this is kind of what's happening here. So you can, this is a kind of a close up of this thing, and you can see these plumes of stuff coming down. Okay, and this is basically a computational thing model of the same phenomenon. So we're not just diffusing down, we're just diffusing kind of in these plumes. And this is one of the unique properties of water. Hopefully this one comes up. So what happens there are actually, in the experiments that you've got in front of you, there are actually two things that are diffusing. Okay? So the red dye is acting a little bit like salt. Okay? There are some dissolved red ions in the stuff, right? And that wants to diffuse down into the clear water below. But there's also heat. Okay? There's heat in the top layer, and that wants to diffuse down. Okay? But the thing is that they don't diffuse at the same rates. And this is one of the really unique properties of water, is that it turns out that heat can diffuse through water 100 times faster than salt. Okay? And the reason for that is because, let me just explain this figure, which you can't see, annoyingly, is that the salt has to move through these large clusters of water that are kind of bound tightly together. Okay? And also, the salt has got water molecules kind of stuck on it because of their charge. Okay? So it's kind of like trying to kind of get through a large crowd at a train station, where the train station is populated entirely by groups of brownies and cubs and whatnot that are all holding hands and being in a group together so they don't get lost. And you're carrying 100 bags. Okay, you're trying to run through that station. It's not possible. Okay, so that would take you a long time. Whereas heat, the way heat diffuses through substances is heat is basically stored in vibrations. This is being video. And to diffuse the heat through, the actual atoms or molecules don't need to move through the substance. They need to jiggle, and they need to jiggle their friend next to them, and then that vibration moves through the medium, moves through the water. So in water, heat can diffuse really, really quickly, whereas salt can't. So what happens is you have some, when I poured the water into your glasses, it wasn't completely flat, and when I put the one glass on top of each other, there were some bubbles, and that made the surface between the two liquids a bit lumpy. So what happens is that if you've got basically a lobe of the hot water going down to the cold water, this will be hot and salty, and the heat can diffuse out of it really easily. So this water here becomes a little bit warmer, but this water here is still salty. Okay? And those dissolved ions in that water, which is now cold, it's now the same temperature as the water inside of it, the only difference is it's got more ions dissolved in it. That makes it heavier, so it starts to sink. Likewise, at the top up here, this tongue of hot water that's up into there, that's hot, but not salty. Okay, and the water around it is so it's cold but not salty. The water around it is warm but salty. The heat diffuses into that, but not the salt. So you can have a buoyant, fresh plume that goes up. Okay, and this basically carries on going as you get a longer and longer and longer kind of lump into these, and you get these very, very long fingers going down through the water. And the really cool thing that this is a process you can see on the scale of maybe a few millimeters or centimeters. This actually happens in the ocean. Okay, anywhere in the ocean where you have warm, salty water on top of cold, fresh water, which turns out to be quite a lot of places. Okay, because the deep ocean is filled from sinking cold water at the poles, which you might have done with Simon already, and the surface ocean is heated by the sun. Okay, and is quite often in places where you have saltiness because you've evaporated the water away. Okay, so that's kind of some of the kind of properties of water due to their kind of basically the hydrogen bonds in water. So the rest of this lecture, I'm just going to be talking about basically some of the water cycle and why the ocean is salty. Okay, so this concept of recycling water. This is quite a neat concept. So water. I use this water cycle, which I guess if you don't need to see the rest of this slide, you can imagine what the water cycle looks like. Water evaporates from the ocean, moves over the land, okay, where it rains out, and that rain interacts with rocks and starts to weather them. Okay, so effectively dissolving the rock minerals into dissolved ions. Those ions basically work their way down into rivers, and although the concentration of ions dissolved in rivers are very low, I mean, it's fresh water. I mean, you can drink it usually. It's not too polluted. They flow into the ocean. Okay, the kind of the first order paradox is here that the ocean is very salty, but the stuff we're adding to the ocean is not very salty. So why is the ocean salty at all? And the reason is we're adding fresh water into the ocean with a very small amount of salt in it. So you think that should dilute the salt in the ocean. But in fact, when we evaporate the water again, okay, we leave behind all of the salt and take away the fresh water. Okay, so although we're adding fresh water and a little bit of salt in, we're only taking fresh water out. So we recycle the water round and round and round and round and round, okay, but the salt only makes it from the land into the ocean. Okay? So the only way that salt's ions are removed from the ocean are in places of the ocean where the water can evaporate enough to leave behind salts, or you remove ions in some other way, either forming shells of kind of bivalves or other corals, things like that form shells, or tests or skeletons. Or you have some chemical reactions where the seawater interacts with the ocean crust. Okay, and these are very, very slow processes. So seawater has got lots of salts dissolved in it, and it has lots of salts dissolved in it because it's a really good solvent. The hydrogen bonds, so the polar nature of water allows it to kind of like grab onto lots and lots of salt ions and kind of stop them interacting with each other, keeps them nice and soluble. And there's this concept of salinity, so salinity is basically the amount of salt. If we had 1 litre of water, okay, it's the mass of ions in that salt, in that water. So I guess there is supposed to be a bottle of water over here. So we have these kind of units. So it's if we had 1 litre of water, it's not, if you dried that water down, how much salt would be left, because that salt that you dried down would have some water hydration in it. It might be that some of the ions that are dissolved in water, when you dry them out, are actually go off as a gas. Okay, but if we could filter the water, so we're just looking at the dissolved kind of stuff in the water, and then make some kind of chemical measurements where we actually add up all of the amounts of the ions, work out how many grams that is per kilogram of water, Okay, so this is doesn't have any units. Right? So quite often you see this term PSU for practical salinity unit. Okay, that's not really strictly correct. Okay, because you've got a mass divided by a mass. So salinity is effectively unitless. Okay, so it's sometimes referred to as parts per thousand. Okay, sometimes you see this symbol, which is the per mil symbol, which is like a percent symbol. It would be shown to you over here if the laptop wasn't retarded. But it's like a percent symbol with an extra zero on it. Okay, yeah. So there's an extra zero here. Imagine there's another one of these circles just here. Damn it. And this is just a map of that salinity in the ocean. You can see it's very similar to the map of temperature. So when the water is warm, it tends to evaporate. That leaves the salts left behind. But you can see that there are some kind of differences. You can see that the Atlantic Ocean is much more salty than the Pacific Ocean. Something I said. And that's because of hurricanes. Okay, so you get a lot of evaporation in the Atlantic, in fact in the Pacific as well. Okay, but hurricanes come into the Caribbean and they've got a lot of fresh water in the atmosphere of a hurricane. Okay, that rains out. And if those rain out over South America or North America, okay, the water flows back into the Atlantic Ocean. Okay, so that won't change the overall salinity of the Atlantic Ocean. Some hurricanes, they make it across the watershed of Central America. Okay, so they're basically exporting fresh water from the Atlantic Ocean into the Pacific Ocean. Sorry, that's fine. It's recorded, except this slide. You can also see some really interesting stuff in the Indian Ocean, which you can't see. But you might just be able to work out where you've got large rivers coming in. So the Congo, the Amazon, are these little bits of blue where we're inputting locally fresh water into the ocean. So we get this kind of, I guess, geographically controlled spatial pattern of salinity. Regions where we've got lots of heat, lots of evaporation and less precipitation, we get higher salinities. We get lower salinities in the higher latitudes where we basically have excess precipitation over evaporation. Okay. And that's what this kind of graph here is showing. So the purple is the salinity of the sea surface, and the dot dash line is an estimate of the latitudinal, so this is summed up at every latitude from the northern hemisphere to the southern hemisphere, what the balance between evaporation and precipitation is. And it largely follows the pattern of evaporation and precipitation. Now, the reason why this is important is because salinity, the more ions you've got dissolved in water, that makes the water heavier. Okay? So this determines some of the physical properties of water, how dense it is relative to the water underneath it, okay, which can determine kind of how the oceans circulate. And that's something you should have covered with Simon, or will be covered with Simon in the physical oceanography section. Okay, the thermohaline circulation is driven largely in part by these evaporation minus precipitation balances. So imagine we take away that boundary between the Pacific and the Atlantic Ocean in Central America. Okay, that means that we're no longer going to have this salinity difference between the two oceans because they can mix between each other. It makes the Atlantic less salty, makes the water less dense. We're less likely to sink and form deep water. Okay, so this is a long-term geological change that might have been driven, but these changes in salinity and evaporation by precipitation can change on seasonal timescales. Okay, so these are all timescales, basically salinity and the density of water is relevant. Okay, so to summarise, coming towards the end of the lecture, so basically what I really want to show is the hydrogen bonds are really important, okay, and they determine almost all of the physical properties of seawater, why they're different from kind of regular other compounds of similar molecular weight, and those things are kind of like the really high heat capacity, high melting point, high boiling point, big difference between those temperatures. It's got a higher viscosity than other liquids. It's got this really weird double diffusion thing. Experiment. So, I mean, the other reason I showed you this is that you can now kind of like do this at home in front of your parents to show, look, I've learnt this cool trick at university. Not that cool, really. So salt helps keep water in the ocean, water and not ice. Also relevant to terrestrial kind of aqueous ecosystems. And the salinity of the surface ocean is determined by this evaporation minus precipitation balance, so we get these quite neat spatial variabilities. Okay, so that's this section. I'll just leave you with this slide here. This is my friend Anton in the cave in Siberia. These slightly fatter sphealing feathers, but these are the cave is so cold that when water drips into it, instead of forming a stalagmite out of rock, it's actually forming these ice sphealing feathers, which is pretty cool. Anyway, so that's those. So we start up again after Innovative Learning Week. I will post hopefully another video for you to watch before the lecture next time, which hopefully will be informative, and I will sort out this stupid piece of shit computer. Okay. Oh, and do vote for a time for office hours if you care about the kind of thing. If you don't care, you can always try and like bash the door of my office down and ask me stuff.